All right, guys, welcome back. We're going to continue our discussion of EIGRP. We're actually getting close to the end of EIGRP. And what we're going to be doing today are two different lessons. We're going to be doing EIGRP Summarization and then EIGRP Traffic Engineering with Summarization. I don't think it'll take 2 or 3.5 hours. Might take 2 hours, maybe 2.5. It depends on how much in-depth we want to get into it. But we're definitely going to be finishing up these two lessons today as part of our discussion, which then leaves us really only 2 other topics left to cover: EIGRP over DMVPN and EIGRP stub routing. And then we're going to start to get into OSPF. Lots and lots of discussion about OSPF. As you can see, quite a bit of information to discuss with OSPF. All right, so let's go ahead and get started. This is going to be the topology that we're going to be using today. It's similar to the summarization topology that we use for other classes, but I've added a few things here because we're going to be taking a look at this configuration in both named mode and classic mode. And we're going to start by really just talking about what is summarization, what do we benefit, what do we gain from summarization, and what are some of the considerations that when we're applying summarization, what are some of the considerations that we need to take into account with regard to EIGRP. It's a completely different process with EIGRP than it is with, say, BGP or OSPF or even ISIS. So we're going to take a look at that today. Let me go ahead and load up my routers here and make sure we've got our console connections to all of our routers. I'm just going to do a real quick cursory check. I did all the configurations for these devices yesterday, but I just want to make sure that we have all of the configurations incorporated here just before we get into our topology itself. So what we should see, I'm seeing adjacencies come up. If I see show IPv6 EIGRP neighbors, yeah, looks like we're good to go. Should have 2 neighbors there, and I should have 2 neighbors here. Show IPv6 EIGRP neighbors. All right, awesome. So we've got our topologies all set, ready to go. Like I said, if you guys want to load that up, you can. I am running GNS3. Let me see what version. I believe it's 2.1.2. Yeah, 2.1.12, excuse me. Obviously, they just came out with a new version, so I may start building the topologies in that newer version for the next session. Certainly for OSPF, I think I'm going to try and take advantage of some of the newer features that are built into GNS3 as part of our OSPF discussion. But anyway, that's what we're going to be working with today. So let's go ahead and get started. All right. Interestingly enough, we're going to be talking about EIGRP route summarization. And traditionally, when we talk about summarization, our focus has always been primarily on reducing the overall size of our routing table. So if I go to my HQ router real quick and just take a look at the configuration, show run pipe section EIGRP, I can see in this particular router, and in fact all the routers, I'm running classic mode for now. I've just got EIGRP for IPv4 running, EIGRP for IPv6. We've got EIGRP enabled on the 3 interfaces that are part of this router configuration, which is this interface here on the left and these 2 interfaces on the right. So we're doing just basic EIGRP in this particular case. But if I do a show IP route EIGRP, we can see that the routing table is pretty significant with regard to size. For a small topology, we've got all these remote networks that we're learning through EIGRP. And obviously the goal here is to identify how we can reduce the size of this routing table. Now, with regard to EIGRP and summarization specifically, our primary concern years ago with summarization was to reduce the overall size of the routing table because we had limited amount of memory that could store routes in the routing table. Nowadays, though, it's really to make the protocol more efficient. We're trying to get to a point where we have sub-second convergence We do that, of course, in EIGRP with the use of a successor and a feasible successor. But in addition, we can make EIGRP more efficient by also creating these summarization boundaries that allow us to take advantage of route summaries to reduce the impact or the effect of topology changes in the overall topology, specifically with the EIGRP because of the query message or the query process that takes place. Now, as you can see right now for the serial or the Ethernet links, we've got equal cost load balancing occurring for these prefixes and these destinations. I actually want to change that effect, and I'm going to make one path more preferred over the other. So this is going to be essentially my primary path, and ultimately this is going to end up being my secondary path. And I want to do that in a way that it's bidirectional and symmetric. I don't want asymmetric routing occurring in this case. So with regard to how we decide to change this, I'm going to really just kind of apply a different delay value for the serial interfaces. Because remember, delay is probably a better metric to modify. It doesn't affect any other process running on the router. And it's a cumulative effect, right? As opposed to bandwidth being the worst bandwidth along the path, and so on. So let's start by just kind of making this secondary path a little bit worse. So I'm going to go into BR2, and I'm going to change the delay on these serial interfaces to 20,010 microseconds. I'm not going to change it by much, just enough to make them unequal costs. All right. So let's go over to BR2. Oops. Come on. All right, we'll start with BRX in this case then. So let's go in interface serial to 1. Again, that's this link here that we're trying to modify. And I'm just going to set the delay on that interface to 20,010 microseconds as opposed to 20,000 microseconds. If I do a show interface serial to 1, we can see now that the delay is 20,010 microseconds. Remember, we're running classic EIGRP in this case, so we're dealing with microseconds instead of picoseconds, but the delay value still affects either one. It's just a conversion factor that we're going to use to put it into the formula in picoseconds. Ah, geez, come on. Control-Shift-6X. That's supposed to break it. 6X. All right. Of course, no IP domain dash lookup would help. There's a reason why I don't want these paths to be equal cost. It's going to allow us to better demonstrate traffic engineering with the EIGRP a little bit later on. And we're also going to be doing a lot of investigation on queries, EIGRP queries, and how those queries take effect. What happens if I have a successor route and I lose my successor route if I have a feasible successor? How does that affect the overall query process? And then on top of that, what happens if I don't have a feasible successor, right? So let's go into interface serial to 1, and let's set the delay here also to 20,010 microseconds. So if I go back to my HQ router now, I should see I'm no longer load balancing across those paths. I'm taking the top path, which is through 172.16.1.2. 1.2 is this router interface right here. This is the 172.16.1 subnet, and it's this router interface right here. By setting the delay on the interface, that affects both IPv4 and IPv6. So if I do a show IPv6 route, EIGRP, show IPv6 route EIGRP, I should see the same thing. That we're going to, the next hop should be .2 for a lot of these subnets or these prefixes. Let me see here. I kind of made a match up here. So if you look at the topology, this loop back here is 10.20. It's 2001 dead beef 20. So that's what I'm looking for here. 20 is right here, and the next hop is Ethernet 1.1 is the exit interface. We're using the EUI64 process. Yes, Mike, I put that on BR2 and BRX serial 2.1. Ethernet 1.1 is the exit interface, which means we're choosing that top path again. Okay. So we really haven't talked about anything about summarization at this point, but obviously one of the benefits of summarization is to make it so all these networks here can be summarized going over to HQ, and we're not sending large routing database information into the HQ router. But there are a lot of things that you need to consider when you're dealing with summarization. A lot of little kind of caveats, a lot of little quirky things that you need to know about summarization in order to really be able to effectively accomplish what it is that you're trying to accomplish. All right, for example, for these loopbacks on Ethernet 1.2, obviously the traffic is going to come through this interface here. It's going to go over the Ethernet 1.2 and it's going to hit BR2 from that side. In fact, let me go ahead and, just so I can make some notes here, go ahead and grab a snippet of this topology so that you guys can see what I'm referencing here. So obviously for these particular subnets here, let's switch to the red pin, we could summarize those networks out that interface. For these subnets here, we would summarize out that interface. And then for these networks, we would probably create multiple summaries to summarize out of both of those interfaces. We'll play around with some different options here because there's lots of different choices that we have with regard to summarization. We're not quite there yet because there's a few other things we have to talk about first. All right, before we get to that point. Okay. So let's first of all investigate whether or not we have a feasible successor. That will be an important aspect to identify. Let's go back to our router here and do a show IP EIGRP topology. And sure enough, for those loopback networks, there's the 10.20. We can see our primary path is through 1.2. The the feasible distance of that path is 232.3456. And then this is 232.3712, so it's slightly worse than the top path. But as long as this number here is less than this number here, we have a feasible successor. So 2298.112 is definitely a feasible successor for 232.3456. Okay. Now let's actually make it so that we don't have a feasible successor. So I'm going to go into BR2 and let's go ahead and go into interface serial 2.1 and let's put in a delay of 50,000 microseconds on that side. Interface, we're already in the interface here, so let's do a delay of 50,000 microseconds on that side and then go back and check our topology database. So now we've lost our feasible successor. Okay. If I do a show IP EIGRP topology all dash links, I can see that that path is still not there. We might still be converging here. That's interesting. Why did that happen? So it looks like we lost our, not only we lost our, we still have the successor route. That didn't change. But why did we lose our, makes sense we lost our feasible successor. Let me try a little bit of a different value. We may have set it above the maximum amount. There is a infinite metric for EIGRP. And we may have reached that limit. So let's go ahead and do 3,000 microseconds. And let's do the same thing on BRX. And go back to HQ here and see what we see. That's really strange. Let me try something here. Interface Ethernet 1.1, we're going to shut that down. Do show IP EIGRP topology. That's weird. So it actually is a valid path. I'm curious why it didn't add it to the topology database. Maybe it was a convergence issue. Let's do a no shut and see what happens here. So we're 2, 2. So we should, as soon as the neighbor comes up, switch back to 1, 2. All right, that's no problem. We've switched back to 1, 2. Now let's do an all dash links and see why we're, that is really strange, because we're not talking about a significant difference in the path. Two, 3, 2, 3, 4, 5, 6, and 2, 2, 9, 7. And let's see what it was before. 2, 5. Let me copy this actually. So that was when we modified the metric there. And let's grab it from here as well. So we're definitely not meeting the feasibility condition. This was the backup path. This was the one that goes over 2.2, and this is the path that goes over 1.2. We're definitely not meeting the feasibility condition here, but it still should show up in the topology database. That's a little bit strange to me, why we're not seeing that. Show IP EIGRP topology. So we certainly wouldn't see it there, but I should see it as part of all dash links. Really, really strange. I'm going to continue on. The reason why I'm going to continue on, because I think the demonstration that I want to run is still going to be adequate. What I need to see is what the effect is of not having a feasible successor. So if I do a debug IP EIGRP packet, debug EIGRP packet, and let's do a query and reply. Okay. Let me do a show debug. So on this router, didn't like that. Let's try that with a reply there. There we go. So I'm doing a query, a debug on queries and replies. Now, from our very first EIGRP discussion, you guys should be aware that query is used in the event that we lose our primary path. So right now, this primary path is available. And I'm talking about specifically this prefix right here, and which is a locally connected prefix on BRX. And what we're going to do is we're going to shut down this interface here and see what the effect of disabling that interface is from HQ's perspective. HQ is going to lose that path. I'm wondering if that's probably the best option. I might shut down this interface instead. Because what we should see then, if I shut down this interface, is that a query should be sent from HQ to BR2 saying, hey, I just lost my path. What is, do you still have a path to that destination? I'm not sure why that path is not showing up in the all dash links. It should be. That's really strange, but in any event, let's go ahead and do that. In fact, let's also do a Wireshark packet capture on this line as well to see if we can see that query process take place in the EIGRP package, or the EIGRP packet stream as well. All right. This is an important concept that we're about to discuss, because you might be thinking about, well, what does this have to do with summarization, and why are we concerned about the query process with summarization? But it's actually a really, really important concept. Okay. So let's let that load up. Eventually it will load. It's just really strange that I'm not seeing show IP EIGRP topology all dash links. Why I'm not seeing that secondary path for this guy right here. Let me try the IPv6. Show IPv6 EIGRP topology all dash links. So here's the 20. Where's the 20? Am I missing 20? No, there it is right here. So we're seeing the same thing with IPv6 as well. The same behavior. I think I know what's happening here, guys. I think I know what's happening. If I go to my routing, my design here, I have a feeling that BR2, we changed the value so much. Oops, let me go to my one I can draw on here. We changed the value so much that BR2 is choosing to take this path to get over to 10.20. And because of split horizon, I'm not going to accept a route coming in that I'm advertising out. So it's a we've modified the value. I might have to shut down. Yeah, I don't know how I could maybe possibly do that. Other than making the overall bottom path just worse altogether. Yeah, I could do that as well. I can make a change on this link and that link so that hopefully this path is not going to be chosen. Because if I go into BR2, I should see that it's going to be going up to HQ. Show IP route 10.20.0.0/16. Let's see here. Yeah, it's going out this Ethernet interface. So that's what's happening. Remember, this is a very important concept within distance vector. I will only advertise the routes that I'm using. Unlike link state, where I'm advertising essentially everything I know about the topology, in distance vector protocols, I'm only going to be advertising the routes that I'm actually using. So because I'm going to HQ to get to those destinations, obviously I'm not going to send a route into HQ to tell HQ, hey, you can come through me, by the way. It won't affect the overall process of what I was trying to demonstrate here from a query perspective, because if the top path goes down, then that's going to affect how BR2 gets to the top as well. So we've got our hello packets, we've got our information going back and forth. Let's go ahead and let's filter on all EIGRP. So let's do apply, let's do protocol 88. So we're not seeing really anything else. So apply, filter, selected. All right, so we're seeing all of our EIGRP traffic in this case. Now, what I'm going to be trying to demonstrate is what happens in this query process from a convergence standpoint. So going back to our topology diagram, I am going to, let me get rid of these lines here. I'm going to go ahead and shut down this interface here. And what I should see is I should see a query coming over the 2.0 subnet over to BR2. And then I should see a subsequent reply from BR2 to indicate that that query was received. Okay? It's really important we understand the query process in EIGRP, and that's really, it is part of this conversation because of how summaries can help us eliminate or establish a query boundary. But we'll go by this step by step here. So let me go ahead and go into BR1 and shut down Ethernet 1.0. Interface Ethernet 1.0. Go ahead and shut that down. And I should see in this case, let's go back to our Wireshark capture. I should see, well, that's interesting. How come I didn't see the query? You know what's interesting here is I'm only seeing IPv6. Oh, that's why. Let me clear the filter here. I need to do and selected. Well, let's, let me make sure I'm picking EIGRP for IPv4. I chose the next header field in IPv6, and we're not presently doing anything with IPv6, so let me go ahead and just filter on IPv4 right now. All right, so I believe that was our first query there. Yep. So here is the query that was sent out. And we can see it's coming from 2.1. Let me stop my capture here. Here's the query that was sent out, and it was sent from 2.1 to this multicast address because this is a multi-access network. Remember, we switched to unicast for point-to-point links, but for our multi-access networks, we stick with multicast as our destination IP for our EIGRP datagrams. All right, so what I should be seeing here, and this is really important, guys, from the perspective of understanding how a query works, is I lost my path to essentially, if you look at the diagram, all of these loopbacks here, these loopbacks here, and this subnet here, assuming I was using that top path to reach all those destinations, which I probably was, right? So I've lost my path to a lot of those individual destinations. Let's see what the query looks like from that perspective. All right, let me pull it up. So I see I'm sending a query. And sure enough, I see all of the routes that are referenced in that particular query. 21, 11, 13, 20. All right. Now, these look like individual, these look like routes that are contained within a single query, which they are. But I need to get a response for each of these routes as well. And if you look at the topology diagram, move this over here a little bit. So 21, let's do this. So 21 is this loop back here, makes sense. 20 is this loop back here. 22 and 23, so we see those loopbacks there. We see 10, we see 11, we see 13, and we should see 12 there as well. And most likely the 3.0 subnet as well. Right there, 172.16.3.0. So that makes sense, right? We lost our successor. We didn't have a feasible successor to reach those destinations. So we had to send a query to router BR2, and BR2 is then going to in turn have to respond to that query saying, I still have a route to those destinations. And if we go back to our Wireshark capture, we can see the reply from here. It's coming from router 2.2, and it's a unicast reply to router 2.1, interface 2.1. And sure enough, in the payload, we're seeing, okay, here's a reply for this route, by the way. That's interesting. We didn't get a reply for all the routes. We got a reply for a single route. And if I continue to go through my Wireshark capture here, let me close that guy, close that guy. You see a reply here. You see a reply here. And I think I stopped it close to that point. So we got a couple more replies. So one reply, another reply, again from the same router, another reply here from the same router, and so on. So what's interesting is that even though the query is a single datagram that's going out to the neighbor, we're sending a reply for different destinations. So that's the 10.20. This guy here was the, can't remember which one it was, 10.21. And this reply here most likely is 23. All right. Let's see, reply. This is the 10.11 subnet. So what's happening is, okay, so this one includes a few others. My point is that we're getting several unique replies for these destinations. So this included 10.12, 10.10, and 10.11, and so on. I guess my point here is that as these changes in the topology occur, these queries get sent out across the network, and we have to reply to those queries within a specific amount of time. The default timer is 3 minutes before we go stuck inactive, and we'll talk about that a little bit later on. All right. We actually have a whole nother discussion about stub routing, where I'm going to get a little bit more into the whole concept of queries and stuck inactive in more detail, but I thought I would let you know about this for now. All right. Here's the other situation about the query process that's really important to understand. If this router queries its peer, then this router is going to query its peer. And if there are other routers down the line, it's going to query its peer and will query this peer and so on. And those queries will run all the way through the network to the edge of the network. And on top of that, before this router can reply, it has to get a reply from that router. And before this router can reply, it has to get a reply from that router. Before this router can reply, it has to get a reply from that router, and so on. So if at any point along this path, if for some reason one of these routers does not reply, then essentially this router is going to have to sit there and wait to reply to the HQ router with the routing information that's available. We talked about this quite a bit actually when we were doing our EIGRP traffic engineering section. You want to make sure that you have that feasible successor, because the feasible successor stops this entire process from taking place. This is one of the only protocols that provides that sub-second convergence if it has a backup path to a destination based on that pre-calculated backup route with the feasibility condition. So really, to effectively scale EIGRP, you need to have feasible successors, and you have to design that into the topology. But that may not always be an option. So you may not have a backup path, which means the query messages are going to have to be sent. So convergence time is no longer sub-second. Convergence time is now a function of the query domain size that you're trying to manage in the topology. All right. So one of the biggest things that you should focus on from the perspective of EIGRP scalability is to minimize the effect of queries in the topology. All right. Queries get generated every single time a route becomes active. So we lose a link to a neighbor, a metric changes for a particular route, a neighbor goes down, a link goes down, whatever it is. If I don't have a feasible successor, I am going to go into the active state, which means I'm basically sending out a query, and then I'm going to have to worry about or focus on reconvergence from that active state. All right? We probably would not be able to see the process of active in our topology because it would happen so quickly. We probably wouldn't be able to identify that it's actually taken place. But it does happen. And depending on the size of the topology, it could vastly affect the overall efficiency of your reconvergence. The other thing about the query process is queries get sent for an exact match of the prefix that you lost. So if I lose route 1.2.3.0/24 and I send a query to my peer, and in fact, let me put this on the diagram here. The way that we could effectively scope this query domain is to terminate the queries based on the fact that we don't have an exact match for that particular path. So let's say in this case, I was somehow over this link advertising the /16 route here, 10.20 10.0.0/16, okay? But on this router, I was summarizing the 1020, 1021, 1022, 1023 into some sort of summary. So I'm sending maybe a 10.20. In this case, it would be, let's see, 12, 13, 14/14. All right, we'll do that calculation a little bit later on. So I'm advertising at 10.20.0.0/14 on this side. If the route goes down, if the longest match route goes down along this path, I will still send a query to the peer. But because BR2 does not have or didn't have previously a specific route to that destination, because we were summarizing it at this point coming in, it's going to stop the query process at that point and say, you know what, I can't, I'm not going to respond to your query because I never had that route in the first place. I had a /14 route and you're asking about a /24 route. Does that make sense? So we can actually design into our topology a way to limit the scope of queries by using these route summaries. That's really, when we get into OSPF later on as well, that's really the benefit that we get from doing summarization, is the scalability factor from a convergence standpoint. Has really nothing to do with reducing the overall size of our routing tables, because routers today can hold tens of thousands of routes or hundreds of thousands of routes with no problem. All right? So effectively what we're trying to do is apply route summarization to break the query domain apart into different query domains. And really, it's not really a function of reducing the size of a routing table. All right. Now, EIGRP does support two different types of summarization. There's auto summarization and manual summarization. Auto summary used to be something that was enabled by default in EIGRP, but version 15 and above, that auto summary feature is disabled, which is really good because it's very rare that we actually need auto summary in any of our topologies, especially this particular topology. Let me demonstrate what auto summary looks like from this perspective, okay? So if I go into BR1, for example, and I'll do this in classic mode, I'll show you guys this later on in named mode, but if I go into BR1, let me do it to HQ first real quick, and show IP route pipe include 10 dot whatever. Okay, so those are all the 10 prefixes that I'm getting. Now if I go into BR1 and go into router EIGRP1, and I do auto-summary, and I do the same thing on BR2, what we're basically saying in this particular case is that we're going to summarize to our major classful boundary. So now if I go back to my HQ router and I look at my routing table, you can see that it is significantly smaller than it was previously. All those 10 subnets are now being summarized as a /8. Well, that's actually probably not very optimal, especially when you consider the fact, if you go back to the topology diagram, we are sending all of our 10 traffic over this link, right? If I go back to my routing table, all right, there's my 10 subnet. Actually, I'm sending it over the 2.2 link, which is, no, that makes sense. 2.0 is the top subnet, I believe. Let me go back to my topology diagram. Nope, it's actually this bottom link. That's kind of interesting. So, excuse me. We can already see that we have some kind of crazy behavior happening here, because HQ is going to get to any one of those 10 subnets going this way, which includes these 10 subnets over here. All right, in fact, if I do a trace route on HQ to 10.10.0.1, let's see what happens. It should go to 2.2 and then go around the serial link, which is definitely not optimal behavior in this case, right? We may actually even lose some packets because of the way Ceph is working and load balancing might be working, but it doesn't appear that we should be load balancing in this particular case. I guess the bottom line here is that auto summary is not typically something that we're going to see because it summarizes to such a major block of addresses, which is not really very practical in most enterprises because we don't have contiguous address blocks that are that large, especially in the Class A space. So our focus is going to be doing manual summarization on our routers and ensuring that we're summarizing to the most efficient summary possible. All right. So it looks like actually we're getting all kinds of weird things happening here, some timeouts and stuff like that. We're getting exclamation H and an asterisk here. So I'll bet you I can't even ping 10.10.0.1. Yep, unreachable. Now I might be able to if I did a no IP Ceph. And see if I maybe, yeah, see I'm getting unreachables because essentially the network is black holed. And that has to do with because, how routers are advertising those summaries. If I go into BR1, for example, and I do a show IP route, you will notice here that not only do we have the local 10 route, there's our 10.10.0.1 right there, but we also have this null 0 route. All right. And when we applied this auto summary feature, it applied to the entire routing process. It didn't apply to a specific neighbor adjacency. So if I go into BR2 and I do a show IP route, all I'm going to have from a 10 perspective is the ones that are connected, right? And the ones that are on BRX. But you'll notice that I'm not really getting any of the 1010 routes because that router is advertising a /8 prefix, and I've already inserted a null 0 route to that /8 prefix locally. So that means that the 1010.0.0 subnet is essentially being routed to the null 0 interface. Moral of the story here, don't use auto summary. So we're going to turn that feature off. Same here. And by the way, it's don't dismiss this as a basic issue. This is definitely something that they could potentially add to either the diagnostic section or troubleshooting section of your CCIE. Seems like a really, really basic concept, but it could really trip you up, especially with the number of routers that you have in the topology and how many points you could potentially see EIGRP running in that particular topology. All right. The other thing that's beneficial about EIGRP, not auto summary, but manual summaries, is they can be enforced anywhere you want because we apply it either in an AF interface mode in our address family configuration, or we apply it on the physical interface in our classic configuration. Whereas in OSPF and ISIS, these are hierarchical protocols, so you cannot summarize within a specific area. Now, ISIS is slightly different than OSPF with regard to how it creates a backbone area, but it still creates non-backbone areas in a similar fashion. And you can only summarize on type 1, 2 routers or ABR or an ASBR in OSPF. And we'll see that later on when we get into those protocols. EIGRP is really a better design choice in a lot of cases for that reason, because it gives you so much flexibility. The topology is actually arbitrary, and so it gives you just a lot more flexibility in how you can implement different features and functions. It's definitely a better choice for like a DMVPN type of design where you have a lot of spokes and a hub in your DMVPN environment. EIGRP is a far better protocol to choose in that type of environment. Okay, BGP is very similar. I mean, BGP is a path vector protocol, but it does take a lot of distance vector characteristics. So it is very similar to EIGRP in the fact that it's arbitrary, but it's a little bit more complex. Okay. If I'm going to run this in named mode, so I'm going to convert BR2 to named mode. because we're going to want to start to look at some of these configurations in both classic and named mode configurations. So I'm going to do a show run section EIGRP. And I'm going to disable the autonomous system for IPv4 and IPv6 for classic mode. So we're going to do config T, no IP EIGRP1, IP router EIGRP1, no router EIGRP1. I had IP in my brain for some reason there. And no IPv6, that's probably what I was thinking of, router EIGRP1. Do show run pipe section EIGRP. Make sure it should have removed the EIGRP from the interfaces as well. Yeah, okay. Because these are all the interface specific EIGRP configurations. So we're going to go ahead and enable EIGRP for named mode in this case. All right. So we need to enable it for this interface here as well as these interfaces there. We're going to use the same autonomous system number, and we'll just do router EIGRP CCIE and address family IPv4 unicast autonomous system number 1 network 172.16. So that's going to include this interface here and this interface here. .0.0. We put our network statements in the same way. And so I should see some adjacencies come back up. And then I also want to run it on network 10.0.0.0, so all my loopbacks are now being re-advertised. Now I need to go to address family for IPv4, excuse me, IPv6. And in this particular case, as soon as I put in the autonomous system, it's automatically enabling EIGRP for IPv6 on all of the interfaces. And we would want to go make those interfaces passive that we don't want to run EIGRP for IPv6. All right. Show run pipe section EIGRP. And we can see that we're running now in named mode on this particular router. Now, the reason I'm doing this is because I want to show you guys, I don't know, again, what they're going to expect you to know for the written or the lab, but I want to show you guys what it is, how the commands are similar, what they look like in both platforms. And we're going to be looking at summaries in IPv6 and summaries in IPv4. All right, so let's go into config T, router EIGRP1, oops, CCIE, and I'm going to go into topology base. It's got to go into the address family first. Autonomous system 1. And I took out the unicast because you actually don't technically need it. It's assumed to be unicast if you don't specify it. Now I'm going to go into the topology base, and you can see here that we have the auto summary command here as well. So it's just a slightly different configuration, but the overall effect is the same. Now, obviously with IPv6, well, maybe it's not so obvious, but with IPv6, there is no auto summary option because we don't have classful boundaries in IPv6 like we had in IPv4. All right, no classful boundaries in IPv6. So we can't really auto summarize in IPv6 in that regard. All right. So let's go ahead and take a look at what some of these summarization concepts will look like. Let me turn off my Wireshark capture. Okay, that's off. And let's start with this group of addresses here first. All right. So we've got our loopback interface that we've got these networks connected to. And I want to create a summary for those particular interfaces. All right. And I want to summarize them effectively to all of my peers because I'm trying to, again, basically reduce the, negate the effect of number one, the number of routes in my routing database, and number two, the effect of topology changes. Now, if you guys recall, with regard to our summarization, we would take each of the networks that we're trying to summarize, And we look for a common bit pattern in those particular networks. So I think everybody agrees that each of these networks here starts with a 10, right? So we know that our summary is going to at least include 10. Now, if I was to convert these bits here, these bits here, these bits here to their binary counterpart, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and then finally 13, 1, 2, 3, 4, 5, 6, 7, 8. So our summary boundary actually lies here. All right? Because again, we're trying to identify what bits are common, what bits are not common. Whatever the common bits are, that becomes my summary boundary. All right? So for this particular set of networks on this client, our summary is going to end up being 10.10 because the value of these bits, actually it would be an 8, sorry. We essentially ignore these bits. So this is the 8th, the 2 to the power of 3, which is 8. So that has a decimal weight of 8. That becomes our common address for each of those octets. And 0.0, and then my prefix is essentially going to be the number of bits that matched. So we have 8 bits here that matched, plus 9, 10, 11, 12, 13 bits here that matched. And you can kind of see that, the common pattern there. So we would be using a /13 as our summary. All right. Now, if I did this with IPv6, it's a very similar process. In fact, it's essentially identical. So we've got 1, 2, 3, 4. This is our 11. This is our 12, and this is our 13. Everybody agrees that 2001 DEAD BEEF is certainly going to be part of the summary in every case. All right. And now I have to convert the 10 to binary. Remember, that is a 10 in hex. Well, actually, technically, it's a 10 in hex. It's not actually a 10 because a 10 would simply be an A. I tried to make it as simple as possible, carrying over the 10, even though a decimal 10 does not result in a 10 in hex, because it should have really been just A, B, C, and D. But you get the idea. So in any case, we can still summarize. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And our 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's see, 11 would be, well, it would be a 1 and a 1, right? Because again, we're not converting it to, it's not 11 in hex. It's actually a 1, 1 technically in hex. Same thing here. This would be a 1, 0. And then finally this, oops. The same thing here would be, oh gosh, sorry about that, guys. For some reason it's not, there we go. The 13 would be a 3, so it would be a 1, 1. So actually in this particular case, our summary boundary lies here because we can see all the common bits for this hextet. All right, those are all the common bits for that hextet, which means my summary in this case becomes 2001 DEAD BEEF colon. Now remember, we've got 4 zeros here, 4 zeros here, so those can be dropped off. We've got 3 zeros and a 1 here, so that's going to be a 1. And then for the last nibble, which is the last 4 bits, the value of these 2 bits is 0. All right, so that's going to end up being 1, 0, double colon slash. So this is 16. This is 48. Sorry, 32. This is 48. 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62. That would be the summary that would include those networks. Of course, you could have subtracted 2 from 64 as well if you wanted to do it that way. I chose to do it the long way. All right. Now, are these good summaries? Do they include the routes that we need included? Do they include other routes that shouldn't be included? Well, let's see. Yes, absolutely. Because this is an 8 and a /13, if you guys recall, would be a 248. So it would be a 255, 248.0.0, and 256 minus 248 is equal to 8, which is our block size. All right. So we're running a summary block of 8 networks, starting at 8, which takes me from 8 to 15. Does that make sense? So we're actually summarizing 8 and 9, as well as 14 and 15 in this particular summary. That's important to note. We'll talk about that in a little bit. In the case of this particular network here, it's a little bit better, but it looks like we're summarizing networks, essentially networks 0, 0 through FF in this case, because the last 2 bits can be anything. And actually, that's not going to work. That's not what I meant to put. We're actually summarizing 0, 0, 0, 0 through 0, 0, 1, 1, which would be 0 through 3. Sorry about that. So actually, this is a pretty good summary, right? Because it actually includes, well, it should include other networks, shouldn't it? Well, no. Here's the reason why, okay? I keep looking at this, and I keep thinking 10, right? And I'm thinking, well, the only way I can summarize to 10 is if I'm doing a block of 2, but that's not really a 10, is it? It's a 1, 0. So just follow the math. The only 2 bits that are not common are the last 2 bits. Those bits can change. They can be anything because we don't care about them, which means that it's 0 through 3 in this particular case. All right. So it's actually not quite 0 through 3 because this bit is turned on, which means that it's technically 1, 0 through 1, 3. If you want to be, more precise, I guess, if you will. Nice thing is it includes those 4 subnets, though, doesn't it? 0, 1, 2, and 3. All right. Because actually that makes sense because we're just talking about the last, essentially 2 bits in this case, are part of the summary. All right. Interesting. Good stuff. So now we've calculated what the summaries are going to be for that top router. Let's go ahead and take a look at the configuration and setting up the actual summaries themselves. And take a look at the effect of those summaries have in the overall configuration. I mean, we could summarize technically down to 0.0.0.0/0 if we wanted to. You can actually summarize to any bit boundary in EIGRP. That's another benefit of doing summarization. The thing that I want to demonstrate, though, is that we automatically suppress any subnets that are going to be included as part of that summary. So any networks that are included as part of the summary are not going to be visible. They're going to be suppressed and removed. All right. Let's take a look at what that configuration looks like in classic mode. Remember, we're now running, in this case, our classic mode on BR1 and named mode on BR2. So we'll take a look at what the configuration looks like on BR2. All right, let's go to BR1. In EIGRP, we summarize to the interface in classic mode. We do not summarize in the process, in the routing process. We're not summarizing an area like we do in OSPF. We'll see that later, of course. We're summarizing to an interface, and the summary always gets applied to the interface that you want to summarize out of. So let's say in this case, we want to go ahead and summarize those loopbacks out of this interface. And what the heck, we might as well do it that way as well, right? Kind of makes sense. Summarize in both directions. No reason for BRX to see all of those unique routes, right? As long as our summary is specific enough that it doesn't cause conflict with the rest of the topology. I picked these subnets down here and these subnets over here for a reason, because I knew that they would not be included in the boundary, all right? All right. So let's take a look at this in our command line. Let's go to BR1 and perform our summary on BR1. So I'm going to go into interface. What was the interface number? Ethernet 10, and I'll do the same thing on serial 20, and I'm just going to simply create the summary. IP summary address, EIGRP1 is the autonomous system number, and I can actually go into my notepad here and just grab this prefix, because you can actually put the summary in dotted decimal notation or prefix notation. So I've created that summary out that interface. I'm going to also do that on interface serial 20, and we'll put the same summary on that interface. You'll notice that we do kind of a graceful restart. It's still nonstop forwarding, so we're not dropping. It's kind of a hitless restart to be able to resync and say, hey, you know, I have some new updated routing information for you, by the way. You know, because of that, I want you to go ahead and resync your database. All right. Now, the first thing that I need to demonstrate to you guys is what happens when I create this summary. All right. If I go into the HQ router and I do a show IP route 10.10.0.0, you can see that it's actually matching against the routing table entry of 10.8.0.0/13. Now, if I did 255.0.0, which was the route that I was previously routing to, that was the unsummarized version of the route, we can see the route no longer exists in the database, and it's being matched against this routing entry of the summary that was created. I can also do a show IP Ceph for 10.10.0.0/24. We can see that that route no longer exists. And let me see if I can do a show Ceph 10.10.0.0. Yeah, that's not going to work. Show IP Ceph, of course, if I say 10.10.0.0 or excuse me, 10.8.0.0. Oh, that would be why. I was wondering why it wasn't showing up. I turned it off. I wasn't even reading the prompts there. Probably should do that on the test. Pay attention to the prompts. Because when it says IP Ceph is not running, that's probably a good indication it's not running. So if I do a show IP route 10.10.0.0, or excuse me, show IP Ceph 10.0.0.0, it should actually show me the same basic concept, right? It's going to say, we're going to go ahead and use this 10.8.0.0/13 route. And by the way, we're going to send the packet to 2.2, and this is the exit interface and so on. All right. So even though we don't see that route technically in our routing table, we can still identify whether or not that is a reachable destination based on the fact that we're receiving the summary. Now, what's interesting is if I do a show IP Ceph and I do a 10.9.0.0, well, guess what? It also is a packet that matches that particular summary. But we don't have a 10.9 prefix anywhere in our topology. Which brings me to a really, really important concept when it comes to summaries. All right. If I do a show IP route, you will notice that one of the types of routes that gets created is this 10.8.0.0/13 route, which shows up as an EIGRP route, but the next hop is our null zero interface. Anytime you do a summary, anytime you summarize routes, you're always going to create a local route for that particular summary to the null zero interface, and this becomes a loop avoidance mechanism. So if somebody in HQ, let me do a debug ICMP. All right, and I do a ping to 10.9.0.1, for example. Of course, it's going to be unreachable, but the ping is reaching BR1 because it's part of that summary. That's really kind of the only downside to summarization, is that you could potentially be advertising networks that don't exist, which means routers are going to think that they can route to those destinations even though they can't. All right. So that was the summary that we did on that router. Again, that's done at the port level, and we summarized all the loopbacks on that router. Let's go ahead and look at the similar configuration on show IP interface brief pipe include 10. So we've got these loopbacks here that we're going to go ahead and summarize. So 10.64, 10.65, and 10.66. So going back to my notepad, 10.64.0.0, 10.65.0.0, and 10.66.0.0. Obviously, these are all going to start with 10. And then we have to figure out what our summarization boundary is. 0, 1, 0, 0, 0, 0, 0, 0 is 64. 0, 1, 0, 0, 0, 0, 0, 1 is 65. And then finally 66. Of course, you could do this in your head, but I obviously want to be able to demonstrate visually what the summarization is going to look like from an IPv4 and IPv6 perspective. So this becomes my summarization boundary. These are my common bits, including the 10, which means my summary becomes 10.64.0.0 slash, we've got essentially 16 minus 2, which is 14 bits that are common, right? Because the last 2 bits are not common. So that becomes my summary, which is 255, essentially 252.0.0. 256 minus 252 is equal to a block of 4. And that's my block size. And that means that that's going to include networks 64 through 67. Right? That's my 4 networks that we're going to be summarizing in that particular case. Now, if I do the same thing with IPv6, obviously we're using essentially the same. In fact, I'm just going to copy this here, just make a modest change. So this is going to be 64, this is going to be 65, this is going to be 66. And we'll just have to do the same conversion here. Again, it's not obviously a hex 64. I mean, it is a hex 64. It doesn't mean it's a decimal 64. So obviously 1, 2, 3, 4, 5, 6, 7, 8. Those bits are going to be off, and then we have our 6 and our 4. It's going to be there. So let's just copy this. All right, and 65 would just be another 1 there, and a 66 would be 2 1s there. So my summarization boundary in this case is here, which means that my summary is 2001 dead beef. And we're going to start with obviously a 6. And this is a 4.
Hey, Scott?
Yes, sir.
Shouldn't it be a 1-0 at the end?
1-0 for which one?
The last
For 66?
summer of it? Yeah,
Are you talking about the V4 or V6?
the V6.
Well,
Yeah, one counts as 2.
yeah, this is a 1 and this is a 2. This is a 4. Oh, you're talking about that one right there, right?
Yeah.
Yeah. Sorry about that. I did a 67 in there.
Good.
Thank you. Doesn't change the math, but I appreciate you pointing that out. So again, so we're now down to a /62 in this case. All right? Because there's 64 bits in this block, or 16 bits in this block, plus the other 48 here is 64, minus 2 is 62. Okay? So pretty much the same math, pretty much the same calculation. The only difference now is we're running in named mode. So how do we apply this summary in named mode? So I'm going to go into router EIGRP CCIE and address family IPv4, unicast, autonomous system number 1. And we're essentially changing the topology base in this case. We're changing how routes are being advertised. So we're going to do our summary address, IP summary. That's strange. Why am I not? Oh, excuse me. I'm going to talk about the summary metric command in a little bit. Actually, because we're applying summaries, just like we always do in EIGRP, the summaries are going to be applied to the interface as opposed to the topology base. Summary metric we'll talk about later. That's where you can identify the seed metric that's going to be used for your summary routes, which is an important concept we'll talk about in a little bit. But I want to summarize out this interface and I want to summarize out that interface, which means essentially I'm creating the summary for all of my interfaces, which means I can use my AF default interface. All right. Should be address family. Oh, AF interface default. Sorry. Default. All right. Now I can do my summary. Should be summary address. Why is it not there? I wonder if it's not going to allow me to do it. Interesting. Let's go into AF interface serial. In this case, we'll go over to 2.1. Yeah, okay, so you learn something every day, all right? So apparently you cannot apply a summary aggregate to the default AF interface, so we're gonna have to do this on each interface. It's kind of strange. It seems like you should be able to just knock it out, but I guess I can understand why they would be concerned about the scope of that configuration. But we're in our IPv4 address family, so let's go ahead and grab our summary prefix, which is their 10.64.0.0/14, and we'll paste that in just like we did before. So it's essentially the same syntax. The only difference in this case is that we're applying it in the address family, AF interface, as opposed to on the physical interface in classic mode. So interface Ethernet 1.2. Excuse me. That's why you don't want to go back and forth between different versions. So let's go back to our address family IPv6, IPv4, unicast autonomous system number 1, AF interface Ethernet 1.0, and we'll do the same summary. All right. Should see that graceful restart again. The neighbors do that graceful restart with nonstop forwarding. Basically, we're withdrawing some previous prefixes and we're adding new prefixes, but it's not going to affect, we saw that up here, the resync here. Doesn't affect overall adjacencies, and it doesn't affect other reconvergence for other prefixes. All right. So now we need to go into our IPv6 address family. Address family, oops, let me get out of that mode. IPv6. You could do unicast and autonomous system number 1 here as well. AF interface serial 2.1. And essentially it's the same command. Oops. The only difference is we're applying a v6 prefix instead of a v4 prefix as our summary. All right. And let's go exit out of there and then go AF interface, Ethernet 1.0, and then the same summary. All right, so if I do a show IP route, we can still see in this particular case that we do have a null 0 route that's going to be created for the summary, so that doesn't change. We still have the loop avoidance even though we're running in named mode. If I do a show IPv6 route, section null 0, I don't know if that'll work or not. Well, we can see it's there, but it doesn't really pull it out for us, so let's just do a show IPv6 route. And we can see the null 0 route. IPv6 is a little bit longer, so that's the one for multicast. There should be another one for right here for the summary that we created as well. Notice the administrative distance of that summary. We see it in IPv4, in IPv6 listed here as a 5. That is the default administrative distance of EIGRP summary routes locally on the router. Now, when it reaches the other router, the route will still show up as an AD of 90, but locally on the router, on this router, that null 0 route takes precedence over EIGRP routes that would be the same because it has an administrative distance of 5. All right. If I do a show IP route 10.64.0.0, you can see the same thing here. Well, it pulled out that one. Let's do /14. 255, no, sorry, 255.252.0.0. There we go. And we can see that the administrative distance of this route is also 5. All right. It's still an internal route. It doesn't show up as an external route, EIGRP route, so it's still an internal route. All right. So if I did a show IP route in this case on HQ, show IP route for 10.64.0.0, we could see that it's matching. That's interesting. I'm still getting a /16 prefix. For 64 and 65 and 66 coming from Ethernet 1.2, so the summary didn't take effect. Thinking. We know the summary is being generated on BR2 because it's showing up. The null 0 route is showing up locally. So I know the summary is being generated on BR2. Let me go back to show IP EIGRP topology and see if I even see the /14 in my topology database. I don't. All right, simple enough. Let's do a show run pipe section router. Take a look at our configuration. There's the 1064 and the 1064/14. And there's the 64/62. And I did the right interface. There we go. I did not do the right interface. I was looking at that interface up there, not the bottom one. Thanks for the catch, guys. These guys are slipping. All right. Obviously, it's not Ethernet 1.0, so we're going to have to change that. Let's go into Ethernet. Let's see here. Make sure I get it right this time. But, you know, this is kind of a good point. I mean, really, it's something we didn't, you know, I should have noticed this before because I was talking about the graceful restart. And I said, you know, we should get a graceful restart. And I didn't get it. And I thought in my head, well, I should have gotten one, but I didn't get one. Maybe I just didn't see it. I'm second guessing myself, right? But of course I wouldn't see it because I didn't have a neighbor on 1.0. So AF interface Ethernet 1.0. And let's do that. Just get that out of there. Actually, let's just do no AF interface Ethernet 1.0. Okay. And let's go ahead and clean up this guy as well. And let's do, I don't know if I can just remove it. Yeah, maybe. We'll see. And we'll do our summary on this interface as well. Oh, IPv6. I'll just copy it from here. Show, and there's a graceful restart. Show run pipe section router. So of course we're going to see the null zero route being created locally because the null zero route is global, right? It applies to the serial interface as well as the Ethernet interface. But I didn't see that on HQ. So now if I do a show IP route 10.64.0.0, I should see it matching the /14 route. All right, and if I do a show IP Ceph 10.64.0.1, for example, if I was going to maybe ping that packet or any packet in that range, it shows me the route, the destination route that's going to be matched against that particular packet. So even if I do 67.24.56, I can see that it's still going to match that particular route. That's kind of another way to test reachability on a router without doing an actual ping to find out what route it would match in Ceph is to just simply do a show IP Ceph and then specify the destination packet and see what route it's going to match in that particular topology. Make sense? Okay. So as far as understanding the configuration, we know, like I said, classic mode, we do that at the port level. In named mode or address family mode, we do it at the AF interface level, which is essentially the same thing in this particular case. We do see the graceful restart and so on. All right. Let me think if there's anything else I want to mention about this particular part of it. I think we're okay in this case. You know, one of the things I showed you guys this a little bit later on, I mean a little bit earlier on, is, you know, how can we use TCL scripts or TCL scripts to be able to facilitate a test across the board as opposed to wasting time and doing individual pings. One of the things that will be your friend on the exam, you don't really need to know the details of Python programming or TCL, but it could definitely help if you want to generate a basic ping script to automate some of the testing that you're doing in the topology, right? You're going to have lots and lots of different routers, and it might take too long to kind of reach different destinations. So what we can do is we can just do like a TCL SH for a shell, and then say for each variable, in this case, let's do 10.10.0.1. So we're going back up to the top router, 10.11.0.1. And all I'm testing is reachability in this particular case to all the loopbacks on that router now that we've implemented our summarization, right? So all I have to do is run that script. Let's see, maybe it's just that. No, that should be it. Oh, shoot. I think I closed it out. Let's try that again. For each var, 10, 11.
I don't think you need the brackets for the ping statement.
Yeah, I think you're right. 13. and close that out. What am I doing wrong here? Should be right.
Missing the dollar sign for the var. Okay.
No, it's there.
Just put the bracket by itself.
Oh, you mean like that? And then do ping $var? Yeah. Ah, the heck. Why isn't it working? So I'm not sure why it didn't work. We had, this was what I typed originally, and this is what I put in to make it work. But in any event, that's essentially how you're supposed to be able to run these tests. Of course, I just wasted a whole bunch of time on my CCIE by troubleshooting a basic technical script, and I could have pretty much done all those pings directly, but let me add 12 in there. But in this particular case, what I'm basically testing is I'm doing a quick ping to 5 different destinations or 4 different destinations. I don't know if that'll save you a lot of time. Obviously, there's more room for potential errors here with regard to entering the script itself, but we can see that we're able to ping all of those individual destinations, even though we don't have those specific routes in our routing table. Okay. All right. Now, one of the other things that's important to understand with regard to these topics that we're talking about, and I was reading up on this the other day about the diagnostic section of the exam. Remember the diagnostic sections, that middle section where you're going to have to answer essentially like regular questions on a test? Well, one of the things that might show up in that diagnostic session is Wireshark captures. They may actually give you screenshots of Wireshark captures and then have you try to identify what's happening based on those Wireshark captures. So being able to look at a query, being able to look at a reply, and inferring information from those captures is really, really important. All right? You need to be able to determine, it may not be related to the query process, it could be something completely different, but you may want to be able to determine what's happening, or you may have to be able to determine in that section of the exam what's happening based on various captures. So it's very important that you guys become really familiar with Wireshark from that perspective, not necessarily doing captures on the exam, the actual configuration and troubleshooting portion, because you're most likely not going to have to do that. All right? Queries are sent. Well, actually, they're not technically sent, but they are sent on a per route basis. So if you lose a link, we know that we could potentially have hundreds of queries or hundreds of replies based on the fact that there might be hundreds of routes behind that particular router. All right, and we already talked about the concept of how queries will propagate based on the topology, and how do we stop those queries from moving beyond a particular destination. So in our particular topology here, let's see if we can kind of simulate this. So we're summarizing these networks here, we're summarizing these networks, but we're not summarizing those prefixes in the back. All right, so what I want to do is I want to create a summary on BR1. Well, you know what? I don't really need to do it. I guess I can just, kind of talk about the concept here. If I summarize these loopbacks on BR1, normally I would summarize them obviously on BRX, but if I didn't and I summarized them on BR1 going out this direction, and this path happens to be the best path for those destinations, well, you know, that's actually not going to happen. I'm trying to think about how I could demonstrate this, how we could define a query boundary with this particular topology. It would be easier with maybe a stub topology, but how I could define that boundary by creating a summary. Let me logically walk through the process. I'm going to demonstrate why this is not going to be the case in this particular case because of the way routing is set up. But let's say that I am advertising a 10.20/14 in this case. So I'm advertising a summary out that interface. and I'm not summarizing on BR2, which means each of these individual routes are going to be sent over to the HQ router on BR2. Now, if this link were to go down, then obviously this router is going to lose its route to 10.20/14, which means that it would send a query if the other path was not a feasible successor for that same destination. It would send a query to that router. Now, this router is not summarizing, so because it doesn't have the 10.20 whatever/14, the query is going to stop at that router, and I'm going to send the reply back. Now, let's go through a configuration, because I want to show you why this would not happen anyway with this particular topology. You guys probably already have a pretty good idea of what I'm about to show you, but let's go ahead and go through the process anyway. So I'm going to create a summary on BR1, and I'm going to summarize. Actually, I can do it on BRX. I'm just going to summarize on this serial interface these IPv4 loopbacks. Okay, so let's go into BRX. BRX, we're running classic mode configuration in this case as well. Show run section router. All right, and we can see we're running a classic EIGRP. So config T, interface, and in this case we're going to go into interface serial 20. And we're going to do an IP summary address EIGRP1 10.20.0.0/14. Remember, we're summarizing 20, 21, 22, and 23, which only includes the last 2 bits that are different. I'm not doing it in longhand because I think you guys pretty much got the idea of how to calculate these. So only the last 2 bits in the second octet are different between these because it includes 0, 1, 2, and 3. So I can just take off the last 2 bits and my summary becomes /20 or /14. 20 would still be set because that would be the 16 and the 4 bit, which does not include the last 2 bits. So it would still be 20 to start with, and it's a block of 4. All right, so we'll go ahead and create that summary. And if I do a show IP route EIGRP, I'll see that null 0 route gets created. There's the 10.20.0.0/14. So you might suspect, of course, on BR1, we're going to see that same route. You might suspect for HQ that we would see that route as well. All right, so let's do a show IP route. Pipe include 10.20. And you will see here that we're getting the /24. In fact, if I just do a 10.2, you can see I'm actually getting all 4 routes here. All right. Now, if I do a show IP EIGRP topology, all right, we see the 24s here as well. There's 22, there's 23, there's the 20. We do not see the /14. All right. Any idea why we're not seeing the /14? Any thoughts? I mean, if I come into BR1, it should be there, right? Oh, let's do an undebug all here. Show IP EIGRP topology. So do I see the /14 in this case? There it is right there. So I'm definitely getting the /14 from BRX, but Mike, you're correct. We always do longest match routing. All right. If the routes are exactly the same, we'll do metric-based routing. If the routes are not the same, we'll do longest match routing. And we're only going to put the information in our database that we're going to use. Unlike OSPF, where we would actually see the summary and the more specific routes, EIGRP is only going to insert into its database what it's actually using to reach a particular destination. Okay? So that's a concern when you're doing summaries. We did the summary this direction, but we did not do the summary this direction, which means that this route, even though it's a better path, even though that top path has a lower overall path metric to reach those destinations, the bottom path is going to be used because of longest match routing. That's what we're going to kind of talk about in the next section as well, which includes how do we do traffic engineering. We're going to talk about leak maps and how can I leak routes out of a summary if I wanted to, say, leak specific routes out of a summary. All right. So we could be really, really generic. We could be more specific. For example, I'm going to go ahead and do this on BRX. Interface serial to 1. Let's do a no summary address. And now let's do a summary address EIGRP1 0.0.0.0/0. And I'm going to actually do that on serial 2120 as well. Interface serial 20. I think I forgot to remove the summary off the other one, but let me, because I think I removed the wrong one. Do show run interface serial 21. 20, yeah. So I didn't take that one off. Let's do, I was in the wrong interface. All right. And let's do show run interface serial 21. So what I'm doing in this case, it's kind of dangerous, but what I'm doing in this case is I am sending in a summary, which is essentially a default route. So I'm basically saying summarize everything in EIGRP to a quad 0/0. So if I go to my HQ router now, show IP route EIGRP, we can see that that route's coming in. It's actually being identified as a default route, as a default candidate, and it's being sent in. So that's one way you can maybe inject a default route into EIGRP without using, well, we don't have default information originate in EIGRP. Sometimes we'll use default network. Other times we'll create a static default route and redistribute it into EIGRP. But they might on the lab exam say, send a default route in from router 5 in EIGRP, but don't use redistribution, don't use the default network command. And you're like, how do I do that? Well, you create a summary route that points to that is a default route. Okay. So it kind of makes sense in this particular case. We're using Ethernet 1.2 to reach that default destination, which makes sense based on the metrics that we've calculated or configured in this particular case. That means that we're going to go this way to get to essentially those loopbacks. And I should be able to ping 10.20.0.1 from HQ and reach that destination. Now, if I do a show IP Ceph 10.20.0.1, we can see that it's matching that default route. It's going out of going to router 2.2 and it's exiting Ethernet interface 1/2. Okay. Can you macro? Mike has a question here. Can you macro the TCL ping script? You mean on the exam? Yes, you should be able to. I believe that they're providing you tools that allow you to create the macros as well. You're talking. I don't know what terminal application they're allowing you to use, but you can create macros to execute certain scripts. And that's a good question. I'm gonna have to research that a little bit, but I believe that you're using standard tools, probably Secure CRT or PuTTY. Where you can create the macros. You could do an alias as well. Yep. I don't know if an alias will allow you to do multiple lines, though. That's an interesting question, right? Certainly we can use aliases to create single command references, but I wonder if you can use an alias to create a tickle script. Let me see here. Let's check that out. Can I use CLI alias to create a TCL script? Let's see. Let's see what they say here. Put open type.
Yeah, it looks like there's a way that if you create a file on the flash, you can alias executing the flash file.
The flash file, yeah. Yeah, that's actually what they're doing right here. They're creating a TCL script, a file in Flash, and they're executing that command. But, you know, honestly, I don't know. You'd have to be pretty proficient at doing it. You'd probably have to have a pretty decent plan of action going into the exam to maybe identify a script that would be useful throughout the exam. And you might end up wasting more time trying to figure that part of it out than just running the regular tests. Yeah. Yeah, so alias, execute. I mean, I guess we could give it a shot. Well, we can't with GNS3 because we don't have Flash. So we can't actually create files in Flash, which actually is an interesting concept because you're using essentially virtual routers in the lab as well. So I wonder if you would even be able to create a file in Flash in the lab. So I don't know, whichever one of you guys go and takes the lab first, I guess you could let us know. I didn't try to do any of that stuff when I was doing the lab. I didn't really see a need for it, quite honestly, because I'm pretty proficient about running individual, testing commands, and so I didn't want to spend a whole lot of time trying to create all these other automation pieces that would take away valuable time for the actual lab. All right. All right, let's see, where were we? Okay, so our idea here, obviously with summarization, we've already talked about this throughout the hour and 45 minutes that we've already been going here, is that we're trying to come up with a way of reducing the scope of the queries in our topology. We're trying to make a disconnect from what the query is asking for and what's being reported in the reply to scope that query. Now you could, if you wanted to, if you have a really, really large topology, you could limit the scope of your queries by running other routing protocols and creating other routing domains. So queries are obviously not going to propagate from a EIGRP domain into an OSPF domain. So we can certainly limit the scope of queries in that particular case. And we'll talk about this a little bit more later on, but there's an issue that we have with regard to whether or not a route goes stuck inactive. Let me show you real quick. Show IP, stop that. Show IP EIGRP topology. You'll notice here that we see these P's next to each of the routing entries, which indicates that these are passive links, right? These are passive connections or passive routes, meaning that we're not actively seeking a way to reach that particular destination. But you'll notice here we see a query, we see a reply, but we also see stuck inactive status, or an S indicating stuck inactive. If I send out a query and I don't get a reply within 3 minutes, the route goes into what we call stuck inactive. And I actually, well, previously this is what would happen. I would actually delete or reset the neighbor relationship for that particular neighbor and try to reconverge to clean out the information that's no longer valid in that particular case. The problem that would happen is that it may not be the direct neighbor that is actually causing that particular problem. I could have some neighbor down here and maybe another neighbor down here, and I'm sending my query over to this router, and then that query is going over to this router, that query is coming down to this router, and so on. So it's propagating through the network, and then for some reason, there's no reply from this router to this router, which means there's no effectively a reply from that router to that router, because I cannot reply to BR1 until I've received a reply from the downstream neighbor. So this link might go stuck inactive, which means that we're going to reset the adjacency between BR1 and BRX, which would obviously affect other routes that I'm trying to learn from that particular destination. All right, even though it was probably not related to any of those routes whatsoever. Now, EIGRP has a secondary process called a stuck inactive query, which gets sent at half the time that the actual stuck inactive timer is set to. I don't know if I can see those timers here. Show IP. I don't think we'll see it in protocols. I'm trying to think of a command. Show IP EIGRP timers. Yeah, okay. Let's see. Obviously, we don't have any active stuck inactive states, so we're not seeing. No, these are snapshot timers. I was trying to see if there was a way that I could see what the default timer was. Let me try something here. Router EIGRP1. I don't think it's going to show the default, but there should be a way to set the timer for active time. So I can set it in limit. I can set the time limit in minutes, but one is definitely not the minimum. Is not the default. It's the minimum. It's not the default. So, from everything that I've taught in the past and everything I've seen in the past, it's been 3 minutes. Of course, it could be version specific, but in any event, we don't reset the adjacency anymore. When we don't get a response to our query, we send a secondary query to the peer called an SIA query. And it's, like I said, it's usually about half the timer of whatever the stuck inactive timer is. Sorry, this one right here. That says, hey, I'm waiting for you to respond to my query. What's going on? How come you're not responding to my query? And that router can come back and say, you know what? It's not me. Yeah, I'm good. I can respond to your stuck inactive query. So now this router says, okay, well, the problem is not with you, so I'm not going to reset that adjacency. Now this router, BRX, would send a stuck inactive query to the downstream neighbor. Assuming that I couldn't get a reply in the first place, I'm most likely not also going to be able to get a stuck inactive reply from that peer either. Which means that if I don't get that stuck inactive reply, then I will reset that adjacency. And then once that adjacency gets reset, I can reply to that peer saying, hey, I don't have a route, or I do have a route, or I would have already replied if I had a route. So yeah, I don't have a route. Go ahead and do whatever you need to do for that destination, that prefix. Does that make sense? You're certainly not going to have to get into a situation on the exam, on the lab exam, where you're modifying those values and kind of dealing with those values. But it's very likely that you'll probably have to design or implement a scenario where you're trying to limit the scope of the queries in some way. And it may not be summarization. It may be through the use of stub routing, which we're going to talk about in our next lesson. Okay? All right. The other thing, we got one more thing that I want to mention before we wrap up this lesson. and then we'll take a quick break, and then we'll get into our next lesson, which is EIGRP traffic engineering with summarization. It's kind of a short lesson, so we'll be able to wrap it up. But one of the things that I wanted to talk about is, what about the metric for our EIGRP summary? So we know we're summarizing these routes here to HQ. And there must be a metric for those routes, because otherwise, how would those routes get sent into, how would I be able to decide what the overall metric is? So if I go to my HQ router and I do a show IP route EIGRP, I can see that there is, in fact, a seed metric for the 1064. We'll go to the bottom one here. Why am I not seeing? I see 2.2, show IP interface brief. And I'm wondering why I'm not seeing that on BR1. Let's see, we should have the summary. Well, I can see it's there anyway. 10.8. Definitely a more specific route. And Ethernet interface is administratively down. That would be why. All right. So obviously I must have shut that down to maybe test a routing scenario. All right. So let's do a show IP route EIGRP. All right, there we go. So we've got our 10.8. It makes sense too, because now we're sending that default route over that top link. I guess I was looking at it wrong the other time, but that makes sense. That's a better metric for that path. We'll talk more about that in a minute here. All right, but I'm getting the 10.8.0.0/13, but notice the metric, 409,600. Now we have essentially in the topology, we have 4 networks that are part of this particular route. This particular summary. The seed metric that gets planted with the summary route ends up being whatever the best metric is for all of those individual routes. Okay? So obviously they're all the same in this case because they're all loopbacks, but we can actually change the metric of the summary route by modifying the metric of one of these routes that are included within the summary itself. So let's just change loopback 0, for example. If I go into BR1 and I do a show interface loopback 0 pipe include BW, we can see that those are the values that we're using for the metric calculation for the loopback. And all I have to do is simply make it look better is to change the delay of the interface, because remember the summary is being created on BR1, so it's just basically the local feasible distance is the connected metric for that particular interface. So if I go into interface loopback 0 and I say delay 1,000, I should see that the metric changes for that particular path. So here it was 409,600. Now it's gone down to 307,200. So it's taking the actual metric, and if I come into BR1 as an example and do show IP EIGRP topology 10.10.0.0 slash 20, well, I think these are 16s. So I can see that the actual metric for this particular path is 25856. Of course, we have to add the link between the HQ and BR1 to get the overall composite metric, but if I do a show IP EIGRP topology, we can see for that 10.8 that it is, in fact, 25856. All right, so if I go back into interface loopback 0 and I say no delay, all right, so now it's set back to its default. I can see that the metric went up to 128256, and if I look at HQ, for the 10.8, it went back up to 128256. So that's a reported distance from BR1 to the HQ router. We're just adding the cost of the link in between to get our overall feasible distance. So there's a couple of reasons why this is important to note. Even though the overall summary won't change, let's say one of those loopbacks goes down, or I'm summarizing 100 different routes, and one of the routes in between goes down, the summary is not going to change itself. However, the route might get refreshed because the metric that was being used was the one that was taken from the route that went down, if you follow what I'm saying. So even though even though our goal is to essentially reduce the impact of topology changes in the network, we could potentially see an issue where the network going down, which is being used to calculate the seed metric for the overall summary, changes the metric of the summary, and we have to refresh the route. Unfortunately, in classic mode configuration, we don't have the ability to change this behavior. And we could see flapping routes if individual routes that are being used to calculate the metric for the summary are going up and down and so on, which means we're going to constantly be churning EIGRP and doing recalculations, even though the goal was to kind of get rid of that behavior. With named mode configuration, though, we have another benefit, right? Remember, we're running named mode configuration on BR2. Another reason to run named mode. So run section router. And I had inadvertently gone in to start configuring this before, but I wasn't ready to talk about it yet. But it's the summary metric command. So we have a summary that's being sent in, much like we saw with the loopbacks on BR1. And again, the metrics of the loopbacks would essentially affect the overall metric of that route. So for example, if I come into interface loopback 0, let's go back to HQ, show IP route 10.64.0.0/14. There we go, sorry. We can see that the metric for this route is 2816000. So if I go to BR2 and I set a delay here of 1,000 microseconds, we should see the metric go down for that particular path. And the metric is, let's see, that is our summary. Why didn't it go down? Show IP route EIGRP 2816000. Let me make sure. Do show IP interface brief. It is loopback 0, 1064.01. Do show run. Loopback 0. Interesting. Show interface pipe include BW. So we do see the delay of 1,000 microseconds for that interface, which should have affected the summary metric on BR2.
Is the bandwidth too high for it to have any effect?
No, it should affect it. I mean, it did the exact same configuration from router 1's perspective. BR1. The only difference here is that we're dealing with named mode instead of classic mode, but delay is always an interface config. Let's go ahead and test that theory. Let me do a show IP route, show IP EIGRP topology. (10.64.0.0) 255.252.0.0. So this is the reported distance. So it definitely went down. Maybe I didn't see, maybe it looked the same, but it wasn't quite the same. Let me take the delay off again real quick. And see what's happening on HQ here. So it's using a composite metric. The reported distance is 256. You know what I think is happening here? I think we're running into the same situation we ran into before, where the delays are being misreported based on the fact that it's a loopback. So let me do this instead. Let me go into interface loopback 0 and set the delay to 100. And let's go into interface loopback 1 and set the delay to 500. Because we're trying to change the pico setting values. Do show IP EIGRP topology. And I should see for those loopbacks, that's the summary. That feasible distance should be less than the rest of them. So 656. Why is it higher? Here's the 66. That's the 66, right? Which I set the delay to 500 microseconds, or 5,000 microseconds, excuse me. Should be this loop back. And then this is the 64. So that's why it didn't change in the routing, because that looks to be significantly higher. And again, it's the lowest value. Why is one so low and one is so high? Show IP route 10.64.0.0. Yeah, that's not going to help. All right, I'm going to try another experiment here. Show IP EIGRP topology. My point is I'm trying to demonstrate that the concept is essentially the same. We can see why the null zero route is taking this number, 163840, because that's definitely the best metric of all the routes that are included. I'm just really confused why this one is so much higher, even though the bandwidth is the same. Do show interface include BW. The bandwidth is the same for all three loopbacks, but the delay is less. That should result in a lower overall metric for that interface. It's really strange. Actually, let's go into interface loopback 0 and do a delay of 10. So we're going to set it to 100 microseconds. All right, so now it's significantly less. Let's look at our topology table. So the null zero route is still taking that number, and 64.0.0/16 is still the same number. Is that the same number? 65617.920? No, it's a little bit higher actually. So that is really strange. All right, let's set the delay to 500. It may not be strange actually. I'm thinking. Yeah, what is going on there? Do show run interface loopback 0, loopback 1, loopback 2. They all have the exact same configuration, yet the metric is being calculated differently. All right, that is very strange. Let's shut that interface down and let's just deal with the other two. So if I go to HQ, what I should see reflected in HQ's route, of course, is that the reported distance should be, basically the reported distance should be whatever the overall metric is for those two loopbacks that are still active, right? Go back to BR2. Do show IP EIGRP topology. And we're seeing 16.384, 16.3840 divided by 128 is 1280. Interesting. It's got to be something to do with the formula and the calculation of the formula, because 65 and 66 are the same, right? 16.3840. So that makes sense. So what should happen is if I go into interface loopback 2 and I set the delay to 10 microseconds or 100 microseconds, I wonder, yeah, tens of microseconds. So now if I do a show IP EIGRP topology, 66. Trying to think, am I calculating am I doing the metric calculation in my head incorrectly? Because it seems like reducing the delay is having an inverse effect on the overall metric, which is counterintuitive to what we're used to seeing, right? The less delay, the faster the link should be. And it seems to be reacting the opposite. It could be a loopback thing. Let me try this on a physical interface and just see. So we've got for Ethernet 1.2, we've got that metric. So that's my Ethernet 1.2. And if I do a show interface Ethernet 1.2 pipe include bandwidth. So we're talking about 1,000 microseconds. So let's make it 100 microseconds. Show IP EIGRP topology. Ethernet 1.2. That is now the metric. So it's got to be a loopback thing. Strange. Because obviously our indication is always that, hey, if the delay goes down, the overall metric goes down, right? But it seems to be reacting differently with a loopback interface in this case. We're decreasing the delay, but the metric seems to be going up for some reason. Oh well. I'm not sure why. There's probably documentation that describes why that's happening, but we're not going to worry about it right now. Anyway, interface loopback 0. We'll do a no shut. So we've got our summary coming in. Regardless of however the metric is being sent in, if these were physical interfaces, we would obviously be able to kind of control that. But we've got our metric coming in, our composite metric. This is the minimum bandwidth for the path. This is the total delay in microseconds for the path, and so on. I was thinking maybe it had something to do with the scaling factor that we were using. Remember, we use a scaling factor with wide metrics. And maybe I was miscalculating something in my head based on the scaling factor, but doesn't appear to be the case. Otherwise, we would have seen the same thing with the Ethernet interface. In fact, let me fix that to do show run interface Ethernet 1.2. No delay. All right. So what I want to do in this case is I don't want the potential, if you will, I don't want the potential of a route that's included in the summary dropping out and it affecting the overall path metric for the summary route, because then that means I'm going to have to do really kind of a useless recalculation, because the seed metric for the summary is really not that critical, I guess, being that it's summarizing all the routes and you know, it's choosing the best metric from all those routes anyway. All right. But like I said, if that best route, if a route that goes down includes that best metric, then we're going to have to do a recalculation based on the summary metric changing. So with named mode configuration, we actually have the ability under our topology base to specify a seed metric for the summary. So let's go into router EIGRP CCIE and address family IPv4, autonomous system number 1, topology base, and we have the summary metric option. So we can specify the summary metric for specific networks, or we can specify the summary metric overall. And let's just say that I specify the summary metric for the prefix that we're injecting. Which one was it? We're in BR2, so that's going to be the 10.64.0.0/14. And now I can set either the administrative distance for that summary route, which is something I cannot do in classic mode configuration. That's kind of nice. And I can also start to specify the actual values that are going to be used for the metric itself. So I can say bandwidth of 1, I can say delay of 1, reliability of 1, load of 1, and finally MTU of 1. And if I go back to my HQ router, I can see now that all those values have been inserted as the calculation for the metric. Of course, we probably broke routing to that because of how large the metric is, but reliability is 1, load is 1, MTU is 1, hop count is 1, and minimum bandwidth along the path is 1 kilobit per second. Of course, you could choose whatever values you want, and you'd want to make them somewhat realistic, but the fact is that no matter what routes are included now in the summary, we're not going to change the overall path metric of the summary route in the event that one of those routes internally goes down, because we're statically configuring the summary metric for that particular summary. All right? Does that make sense? So that's kind of our initial discussion. That actually took a little bit longer than I thought it would, but I think it's good information. You guys have any questions before we wrap up this lesson and then talk about going into the next lesson here? Any questions at all? Okay. Definitely need to be aware of how summaries are created, both the name mode and classic mode, what the overall effect of creating a summary is on your query domain, as well as routing from a perspective of longest match prefixes and longest match routing principles. And kind of an interesting way of injecting a default route. I'll show you guys that again, because you might say, well, wait a minute. Yeah, great. You injected a default route, but I lost all of my other individual routes because they all got summarized. Well, you can use leak maps to prevent that from happening. So we'll talk about that in the next section, which then means that we're really truly generating a default route into EIGRP and not losing any visibility on our longest match route prefixes. All right, so we'll wrap up this lesson. See you guys in the next one.